Hello. In the last lecture, we discussed how to derive the Euler-Lagrange equations when the functional involves an integrand which depends on the function y and its first derivative as well as a second derivative. For the first derivative, we did a small example which is to prove that in a plane, if we are given 2 points, the curve of least length going through those 2 points is a straight line. That is an obvious result, but we were able to verify that using calculus of variations framework. And then we considered a functional of this form that I will write is minimizing a functional j, which is now in the form of an integral x1 to x2, where the integrand depends on y, y prime and y double prime dx, and this is minimized with respect to y of x. And then we wrote Euler-Lagrange equations for this problem, and we also considered an example that looks like this. The example that we considered was a beam where the boundary conditions we do not say what it is right now. When it deforms, let us say it deforms to some form like this, where this thing is w of x, that is if x goes like this, let us say x equal to 0 at this end, 0 at this end and x equal to L at this end. We want to find this function, w of x. Let me erase it and write it properly. So, this function w of x, okay, that is the unknown. So, there, like we have written this minimization problem, now we say minimize with respect to w of x, that is the function that we do not know. Instead of j, we have the functional which is the potential energy, because you may recall that variational methods are also called energy methods. So, here we have potential energy P E, which is defined as an integral 0 to L, and the integrand we had written this E I w double prime square by 2 minus q w dx. Okay. Q here is the force that acts on the beam. Okay. Some force like this acts on the beam, which is a function of x, q of x, and E is Young's modulus of the material of the beam, Young's modulus. I is the second moment of area of the cross section, second moment of area of the cross section of the beam. Okay. We will discuss later where this comes about. Okay. First, let us take this problem and try to minimize it. Okay. If you remember the Euler-Lagrange equation, so the necessary condition for this w, what when you say w want to find, we actually want to find the w star of x, that deformation. So, this beam under some boundary conditions which we will come to later, under the given loading q of x, it should give us the minimum value of potential energy, local minimum potential energy, and such a thing w star is what we want to find. In other words, the beams that deform know how to solve calculus of variations problems. So, here we have Euler-Lagrange equation, okay, and that one, if you recall, it was dou f by dou y, in this case it will be w, minus d by dx of dou f by dou w prime plus d square by dx square of dou f by dou w double prime equal to, that is a differential equation. Our f is this. Okay, this is our f. We see that f depends on w. So, dou f by dou w is going to give you minus q, and this f does not have dependence on w prime. So, that is equal to 0 plus d square by dx square of dou f by dou w double prime, which is there, that 2 and square 2 they cancel. So, we will have E I w double prime equal to 0, which gives us, if I take this q the other side because minus q, I will have d square by dx square E I w double prime equal to q. Now, if you assume that E and I, that they do not depend on the x, that is their constant cross section, then we get E I fourth derivative, solid double prime second derivative, and then you have two more derivatives, d to the 4 w by dx to the 4 equal to q. This is for general. Okay, this is for general, where you have E and I vary with x, and this one is for constant E and second one of area I. This is a familiar relationship for us from the Euler-Bernoulli beam theory, which we got it from minimization of potential energy. Okay, this much we had done in the last class. Now, we will try to write the boundary conditions also. The boundary conditions were, there were two sets of boundary conditions. One was dou f by dou y prime minus d by dx of, for a general integrand that have y I am writing, dou f by dou y double prime times h evaluated at the two ends x1 x2 equal to 0, and we also had this dou f by dou y double prime into h prime, again evaluated at the two ends equal to 0. This is what we had. Okay. Now, again let us see what f is for this problem. F is, and y, instead of y we will have w in this problem, that is E I w double prime square by 2 minus q w, right. Based on that, let us write this boundary condition. There is no w prime, so that is 0, minus d by dx of dou f by dou y double prime, that is dou f by dou w double prime, that gives us E I w double prime times h is equal to 0, that is from 0 to L, that is at 0 as well as L, and this one is E I w double prime, which we just did this thing over here based on what f is. Instead of y we have w multiplied by h prime 0 to L equal to 0. Now, let us see what this means. If w is specified, h is equal to 0, h equal to 0, like we had done in the case where integrand depends only on y prime and not y double prime, h is equal to 0 if w is specified. Okay. If it is not specified, then this thing has to be 0, and this particular thing minus does not matter because it is equal to 0. This is if you assume constant I and constant E, that will simply become E I triple derivative, okay, because this already double derivative and then we are taking d by dx, assuming that E and I are independent of x, that is their constant. Then this one we are writing again, this is for constant E and I. Okay. So, for that we can actually interpret this again from beam theory, if you recall, that is nothing but the shear force. The shear force, a bending moment diagram we do, that is the shear force. Likewise, this particular thing here is bending moment, because W double prime is proportional to curvature and curvature is proportional to bending moment. That is our Euler-Bernoulli beam theory. This is bending moment. Okay. So, if you look at this H prime, this H prime is equal to 0 if W prime, that is the slope of the beam, is specified. Okay. So, you can see the connection between the boundary conditions which are essential, that is H or H prime being specified means that or W prime are specified, they are essential boundary conditions or Dirichlet boundary conditions. When they are not specified, the corresponding ones, in this case the shear force and bending moment are 0. Whenever H is not specified, W is not specified or H is not equal to 0, according to the boundary condition E I W triple prime for constant E and I must be 0. Likewise, if W prime, the slope is not specified, corresponding bending moment should be equal to 0. So, what we are saying here is that if I take a beam, whenever I talk about beam, so first thing we talk about is cantilever beam. It is fixed here and then free here. When you say free here is what? W and W prime are not specified. They can be anything as per the loading applied on this cantilever beam, and fixed means that W is equal to 0, W prime is also equal to 0. That is why when this beam bends, we have to make sure that W is 0 and the slope is also 0. We have to go with slope 0 there. But at this end it can be anything. Okay. So, here we have W is equal to 0, W prime equal to 0. That means that if we go back and look at what we have, when W is specified, equal to 0 in this case, the shear force need not be 0. It can also be 0 in special cases, in general not be 0. Similarly, W prime slope is specified by a cantilever beam over here, then the bending moment need not be 0. It can also be 0, but need not be 0. Okay. But if it is free, W not specified, then the shear force should be 0 at this point, and so should be the bending moment. Both shear force and bending moment are 0 here. Okay. So, that is how the boundary conditions also follow from calculus of variations. We can take any other boundary condition. So, we can take, let us say, the simply supported beam. So, we have a pin joint here and we have a pin joint with a roller support over here. This is what we call simply supported beam. Here W is specified, whereas W prime is not. Here also W is specified, W prime is not. What this automatically means is that since W prime is not specified, the bending moment here is 0. Bending moment is equal to 0 because W prime is not specified, because W prime is not specified. Okay. And the same thing here, again bending moment must be 0 here, bending moment must be 0 here, because that is our boundary condition. When W prime is not specified, this must be equal to 0. Okay. So, based on this you can consider various boundary conditions. Let us say we take this boundary condition, let us say fixed on one side, and this side I would let it slide along a vertical axis with a block moving. So, here W is not specified, it can be anything. Let us say I apply some loading here, it is going to move, right. So, W is not specified at x equal to L, but W prime is specified because it is a block moving here, and that block has to slide vertically. So, it does not allow the beam to rotate there. W prime equal to 0. W prime equal to 0 means that bending moment there need not be 0. So, implies that bending moment need not be, I should say, bending moment need not be 0. Since W is not specified, then the EI W triple prime, which we said is shear force, okay, that should be 0 because W is not 0. Okay. So, the Dirichlet and Neumann you can specify only one, either Dirichlet or Neumann, meaning either essential or natural. The fact that here whenever W and W prime are not specified, automatically these things becoming 0 are called natural boundary conditions or Neumann boundary conditions. Naturally it happens, natural or Neumann boundary conditions. Okay. So, likewise you should try a number of beams, because you can have a number of boundary conditions for a beam. So, we have considered fixed, free, pinned, guided like we have shown, and you can have guided with, okay. So, that is this particular one is going to be like this, there will be a pin and this one is guided vertically. Okay. You can have all different boundary conditions and then write the appropriate things based on whether W is specified or W prime is specified. Okay. So, this way we are able to solve the functionals that have two derivatives. Let us go one step further. We had first derivative, second derivative. Now, let us see if we have third derivative, what happens. Let us say I take a j where I have x1 to x2 f y, y prime, y double prime and y triple prime dx. Okay. Again, if you recall how we did Lagrange equations to convert that to first, not this actually, let us first do this necessary condition, that is the Gauss variation y and h, okay, that is an integral still x1 to x2 dou f by dou y times h plus dou f by dou y prime h prime plus dou f by dou y double prime h double prime dou f by dou y triple prime h triple prime dx. So, we have to do one integration by parts to get that to h, so that we can apply the fundamental lemma of calculus of variations, and we have to do integration by parts by twice to get this h double prime to become h and the boundary conditions. And now, For this one you have to do integration by parts 3 times. So, you have to do integration by parts thrice, okay, which you can do for one to get some practice, but we thought that we can actually see some pattern. So, when we had an integrand which depends on only on y and y prime, our Euler Lagrange equations look like dou f by dou y minus d by dx of dou f by dou y prime equal to 0. Similarly, if I had integrand y, y prime and y double prime, that gave us dou f by dou y minus d by dx of dou f by dou y prime plus d square by dx square of dou f by dou y double prime equal to 0. That is what we got. Now, there is a pattern, meaning that when we had a y and y prime, that still has only 2 terms, the same 2 terms. Because presence of y double prime, we got an extra term. There is a plus, minus, plus, and derivative order is increasing. So, if we have 3 derivatives y, y prime, y double prime and y triple prime, then it is, we can see the pattern. We can also do the long winded way, doing integration by parts as many times as required, or we can write this as dou y by dou f by dou y d by dx of dou f by dou y prime plus d square by dx square of dou f by dou y triple prime, then minus. So, here we had double prime, not triple prime. This is double prime, this is dou y double prime. Now, it will be minus third derivative d cube by dx cube of dou f by dou y triple prime equal to 0. We have seen the pattern now. We can do the long winded way and find that this is what will happen. Okay. So, in fact, when you take n functions, the same pattern will continue, plus minus plus minus plus minus dou f by dou y, y prime, y double prime, y triple prime and so forth. So, let us do a shorthand notation, so that we do not have to write this. F sub y means that it is dou f by dou y. Okay. So, this is f y, and then next one we will write f y prime for dou f by dou y prime, and then we would put a prime there. Okay. Plus we can write f y double prime, and then we will say double prime of that d square by dx square minus f y triple prime, and then triple prime of that. Okay. So, each time whatever you take, you have to take that derivative y prime prime, y double prime prime, y triple prime triple prime. It is a consequence of how many times you do the integration by parts. Okay. Based on that, if we have a functional whose integrand has, let us say y, y prime, y double prime and so forth up to y nth derivative. Okay. I am writing it as in brackets n. If we have the Euler Lagrange equation for this, that is differential equation or Euler Lagrange equation for this, turns out to be, basically I can write all of these one at a time, or I can do it in the form of summation, where I have to go, if I have n, I will have up to n derivative, because when I had only one derivative, I had right. I had d by dx dou f by dou y prime. Okay. Now, we have 2, then there will be 2, 3 and so forth, right. So, we can write this general equation in the notation that we have, right. So, you can say f, we have to take the derivative where we have, let us say I equal to, we have to see because there is y, there is nothing. So, I will put 0 to n equal to 3, this is this I equal to 0 here, I equal to 1 there, I equal to 2 there, I equal to 3 there. So, I have to go 0 to n, 0 to 3, and let us also take care of the sign. Okay. Let us take care of the sign, which is minus 1 raised to I, because the first term has positive sign. So, minus 1 raised to 0 is 1, and then when it is I equal to 1, that is a minus sign. So, minus 1 raised to 1, which remains minus 1. When I equal to 2, that is this term, that is third term here, that will become positive, negative, we have that, and then we have f y. I will indicate this as we are taking derivative y prime by w prime and so forth, and all of this we have to take derivative I times equal to 0. Okay. So, if you take this from n equal to 3, then we get this. In this one, if I put n equal to 3, then I am going from 0, 1, 2, 3. So, I have 0th here, and then the first term here, and then second term here, and the third term there, and the sign of it is a minus 1 raised to 0, 1, minus 1 to 1, negative, and then positive, and then negative, right. So, that is how we get. So, this will be the general form of the Euler-Lagrange equation for an integrand that has n derivatives. This general form can also be written for the boundary condition. So, this is the general form of Euler-Lagrange equation for integrand involving n derivatives. Okay. Similarly, the boundary conditions can be written. Okay. Again, you have to work it out one by one and see the pattern, but once you find that pattern, you will realize that it will look something like this. You have I going from j to n, and you will realize why we write it like this, minus 1 raised to I minus j f y I raised this whole thing derivative up to I minus 1, and all of this, okay, including the summation, times what we had h, that is also taken a derivative j minus 1 for j equals 1, 2 up to n. Okay. So, j goes 1 to n, meaning that if I have only y prime, that is n equal to 1, I will only one boundary condition, okay, which if you recall, okay, let us keep this, the boundary condition when n is equal to 1, meaning that my integrand was f y y prime. If I have that, our boundary condition was dou f by dou y prime into h at the either end, x1 x2 equal to 0. So, I should actually put equal to 0 there, and this is evaluated at x1 and x2, they are boundary conditions after all, that is what we have. So, what do you have here? When n equal to 1, you are going from I equal to j equal to 1. So, this is n equal to 1 here. So, I have to go I equal to how many conditions? First of all, I will have j equal to 1 to n. So, here I have j equal to 1 only, because that is the n also here. So, I will only one boundary condition, which is this. So, now I should go from 1 to 1, because j equal to 1, that goes up to n, n equal to 1, 1 to 1 meaning only 1, minus 1 raised to I minus j. Both I and j are 1, 1 minus 1 0. So, I get a positive sign minus 1 raised to 0, and that is a positive sign. And then f y I, right, that I equal to 1 now, because I goes from j to n 1. So, I have y prime dou f by dou y prime. That derivative should go to I minus 1, I equal to 1, that is 0, we get this, right. Now, if n is equal to 2, you can verify this, then I have f y and y prime and y double prime. Then if we recall, we had dou f by dou y prime minus d by dx of dou f by dou y double prime multiplied by h at x1 x2 equal to 0. That is what you will get, but now j equal to I equal to j to n. Now, j we have to try for j equal to 1 and j equal to 2 as written here. So, we get that j equal to 1 we get 1, j equal to 2 we get another one, that other one is dou f by dou y double prime into h prime again at the two ends x1 x2 equal to 0. So, here I have to do j equal to, this is for j equal to 1, this is for j equal to 2, right. If j equal to 2, you have to go from I equal to, so I think it may be the other I, yeah. So, j equal to 2 here. So, now I goes from 2 to 2, that will only get one term here. J equal to 1 means that you will have two terms coming. So, we have the first term and then second term, right. I minus 1, so that is the first one, I equal to 1, that will be no derivative there, otherwise we have 1 d by dx as this one is showing. Okay. So, the general form of the equation, differential equation which we have here, as well as the boundary conditions, if we understand that boundary condition will be as many as the number of derivatives. So, we have covered all of the general thing in terms of many derivatives of the function. Next, we will consider what happens when you have multiple functions, and then we will do a couple of problems.